of the most intriguing is one of the most intriguing problems in particle physics today, and it has to do with the fact that whereas in the gauge and Higgs sector of the Standard Model, we only need few parameters, actually 4 couplings and 1 mass scale, to describe a huge variety of interaction, all gauge interaction of 3 family of quarks and leptons. Instead, to describe fermion masses and mixing angles, we need up to 22 additional parameters. And since we have 3 generations of fermions coming into 4 different species, 2 different charges for the quarks and 2 for the leptons, we need up to 6 plus 6, 12 masses, essentially 1 parameter for each mass, then 3 plus 3 mixing angles, 3 mixing angles for the quark sector and 3 mixing angles for the lepton sector, 1 CKM phase for the quarks, and up to 3 phases for the lepton sector. Okay. And these are essentially all free parameters in the Standard Model, so a huge number of free parameters. Moreover, related to this, we have an additional parameter and an additional problem, which is the strong symmetry problem, namely the fact that whereas the CP symmetry is broken by essentially at order 1 by the CKM phase in weak interaction, instead the possible CP violation in a strong interaction that is related to this particular combination of parameters, the topological angle and the quark masses, is bound to be extremely small, no? Below 10 to the minus 10 by the electric dipole moment of the neutron. Okay, what are the options to try to address this puzzle? Essentially, we have 2 possibilities. Either we go top down, we start from a fundamental theory like string theory, and then we try to derive essentially the consequences of this theory, and we try to compute fermion masses and mixing angles starting from the first principle. However, this direction is not so easy to follow because you know that we have a huge number of vacua of this theory. Each vacua essentially defines a different low energy effective theory, and so this task essentially is at least today is a almost impossible task. The other possibility is that we go bottom up. We start from the data and we try to build some effective field theory, trying to explain the data and also trying to avoid the so-called swampland region, that is the region that apparently is consistent with the building blocks of an effective field theory, but it is not consistent with the general principle of the fundamental theory. In this talk, I will follow this second approach. And one of the few tools that we have in order to address the flavor puzzle following the bottom-up approach is the one relying on flavor symmetries. And the big motivation, the strong motivation to use symmetries to address this problem is the striking success of the symmetry principle in explaining the features of fundamental interactions. Here I have listed just a number of examples that play a key role in explaining general relativity, in addressing the problem of particle classification and in shaping our current view of electroweak and strong interactions. The flavor symmetries have this peculiar property that they are horizontal, so they act in generation space. Let me give you a simple example. Suppose that this flavor symmetry is a U1, so we have to assign charges to the different fermion fields. Let me concentrate on the lepton sector and let me assign charges in such a way that we have only a vanishing combination of charges, that is the sum of the charges in the third generation. This is equal to 0. This immediately implies that the charge lepton mass matrix has this particular pattern. You see there is only one entry that can be different from 0. And this describes a tau, a massive tau, and massless electron and mu. Now, this simple example already displays some general feature. Namely, we can go relatively close to the data, to the reality, because after all, this is not a bad first-order approximation. No, we know that the electron and muon are much lighter than the tau. Moreover, this has the nice property that until the symmetry is unbroken, this texture is stable under a quantum correction. But already from this example, we see a general feature, a feature that applies to all flavor symmetries, that necessarily we need some correction in order to get, to go, if you wish, from this first order approximation to a realistic description of fermion masses. So we need the corrections, and we learn that flavor symmetries are necessarily broken. By the way, stop me at any time if you have some question. So, since we have to break the symmetry, we need a symmetry breaking sector. Such a symmetry breaking sector usually consists in a set of dimensionless gauge invariant scalar fields. Dimensionless simply because I measure these fields in units of some fundamental scale that are charged under the flavor group in such a way that when they acquire a vacuum expectation value, they break the flavor symmetry. If these order parameters are small, okay, then we can expand the quantity of interest, namely the mass matrices in power of these symmetry breaking parameters. And we have a first term, the term which is of order 0 in tau, which is nothing but the symmetric limit. No? In the example I gave you before, this corresponds to this matrix. And then when we turn on the correction, we end up with an expression of this type in which we have terms of order tau or of order tau square and so on. Now you see the problem of this type of approach. Usually, if we want to have a realistic description of masses and mixing angles, we need at least a few terms in this expansion, which means several free parameters. Additional parameters can also be present because, for instance, we should take into account renormalization group corrections or supersymmetry breaking effects if the theory is supersymmetric. Moreover, we have an additional problem, namely the fact that these symmetry breaking parameters should have a a particular size and a particular direction in flavor space in order to do the required job. So this is the so-called vacuum alignment problem in the symmetry breaking sector. And on top of that, we can also have a huge number of possibilities because we can choose the flavor group in many different ways. This group can be continuous, discrete, global, or local. And in the end, we have many, many models, many successful models that work in describing fermion masses, but not a baseline model that can be singled out in this variety of possibility. So to summarize, the usual path is the following one. We choose some flavor group. We assign fermions to a group representation, if you wish. And then at the end, we look for some symmetry breaking sector in order to turn the unrealistic first order approximation into a realistic model. So you see that in a sense, the crucial sector, no, the symmetry breaking sector in this pattern is relegated to the last step. And in this talk, I would like to see if it is possible to reverse this logic and instead of starting from the flavor group, to start really from the symmetry breaking sector, namely to start from the fields that parameterize the vacua of the system. Let me call moduli space this manifold that parameterize the possible vacua. And so I would like to see if starting from this manifold, it is possible to reconstruct this pattern, for instance, to identify some flavor symmetry group. Let me give you an example, a toy model, an example which is not realistic. Suppose that the vacua of the theory are in a one-to-one correspondence with the unoriented lines of a plane that goes through the origin. So we ask how can we parameterize such a manifold? Well, we draw a circle which is a center at the origin, and each point on the circle identify a lines of the plane, so identify a possible vacuum. But we immediately realize that this description is redundant because two points that are opposite in this circle actually represent the same line. You see that we have a kind of symmetry, a parity symmetry, as a two symmetry, which indeed is not a true symmetry, is something related to the redundancy in our parametrization. So is what we call a gauge symmetry. Actually, the situation is completely analogous to what we have in the electromagnetism, if you wish, where the same electric and magnetic field can be described by an electromagnetic potential, which are related by a gauge transformation, okay? Here the role of the gauge symmetry is the U1, and also this is not a true symmetry, is something that is related to the redundancy in our description, is what we call a gauge symmetry. As we do in the case of the electromagnetism, in which we can choose a gauge, also in this case we can choose a gauge and we can single out what we call a fundamental domain, which is a portion of this circle that is sufficient in order to cover all the vacua of our theory. Now, let me give you a less trivial example that is directly related to modular invariance. Let me start from string theory that is defined in 10 dimensions. 10 dimensions are too many, so we need to compactify 6 dimensions. And the simplest compactification is on 3 copies of a torus. Okay. Actually, a very convenient way of dealing with a torus is to think to a torus like a lattice that is defined by a basis of 2 vectors, omega 1 and omega 2. And the way in which we see that we can identify this lattice with a torus is to take a unit cell and to identify the opposite side of the cell. You see, if we glue, for instance, this side with this side, we obtain first a cylinder. And then if we glue the circles that are at the opposite edges of the cylinder, we get a torus. Okay. Now, up to rotation and up to dilation, the tori are parameterized by a complex variable, which is called the modulus, that lives in the upper part of the complex plane, and that it is simply the ratio between these two basis vectors. Now we have essentially the same problem as before, because it is true that tau identifies a torus, but this description is highly redundant. And this is redundant because we can, if you wish, choose another basis that identifies the same lattice. We can perform a change of basis in the lattice, but the lattice remains the same. And this change of basis is reflected in this parameter tau as a linear fractional transformation of this type, where A, B, C, and D are elements of a 2 by 2 matrix that are integers and have a determinant equal to 1. So indeed belongs to the SL to Z group, which is the modular group. Okay. The modular group is a discrete but infinite group. It is generated by 2 elements. One is the translation, sending tau into tau plus 1. The other one is the so-called duality transformation, sending tau into minus 1 over tau. And as we did before with the toy example, instead of dealing with the entire upper part of the complex plane, we can make a gauge choice and restrict ourselves with a fundamental domain that consists in this strip that I have depicted here. Okay. Now, in any particular point of this strip, modular invariance is completely broken, which means that if I start, for instance, from here, and I perform a modular transformation, I go outside this strip. For instance, with the T transformation, from here, I go here, okay, and so modular invariance is broken. There are, however, 3 exceptions that are called fixed points, in which not the whole modular group, but a part of it remains preserved. For instance, let's see what happens in this point, which is the imaginary unit. Okay. Of course, if I do a translation, I goes into 1 plus I here, and so translation are not preserved. But if I perform a duality transformation, I goes exactly in I. So this particular point preserve the transformation S, and so there is a residual symmetry that actually is a Z4. Okay, so any of these points preserve a particular finite subgroup of the modular group. Similarly, I can define also CP transformation. CP transformation send tau into minus its complex conjugate up to modular transformation. And again, in any point of this fundamental region, essentially CP is broken, but along these particular pink lines in which CP is unbroken. For instance, along the imaginary tau axis, you see that essentially tau remains the same. And also, if I am along the border of the fundamental region, CP is conserved because I can combine it with the modular transformation. Okay. Now, we have almost all the elements to define modular invariant theories. And let me now do this in the framework of supersymmetric theories. So you should understand really these fields as supersymmetric multiplets, or if you wish, chiral multiplets in the technical sense. So now tau is a chiral multiplet that undergo this particular set of transformation. And if we have matter multiplets describing fermion and bosons, we should define how the modular group acts on these matter fields. First of all, as in the usual, let's say, framework of traditional symmetry, we can transform any multiplet with a unitary transformation of the group. However, there is a technical problem because the modular group is an infinite non-compact group, so it does not allow unitary representation. So instead of putting here a unitary representation of the modular group, we should put a unitary representation of a finite copy of the modular group. Now, there is an infinite sequence of finite copies that are the so-called finite modular groups that are characterized by an integer label, which are called the level of the representation. And by the way, for the first few levels, these finite modular groups are close relatives of well-known groups that have been used heavily in model building precisely to try to describe fermion masses. Essentially, these are small permutation groups that are also the isometries of the Platonic solids. Okay. So here we have a unitary representation characterized by the level. This is not the end of the story because we have also, if you wish, an overall factor, which is called automorphy factor, raised to some power, and this power is called the weight of the representation. So this is the most general way in which we can transform matter fields, okay? We have the level, we have the representation at this level, and we have also this weight. And now, fermion masses in these theories have this particular structure. They are essentially given by the Yukawa couplings that are holomorphic function of the modulus because they come from the superpotential, times factors that are wave function renormalization that are not holomorphic coupling. They depend both on tau and tau bar that essentially are due to the transformation that are needed in order to put the kinetic terms into canonical forms. So this is the general structure of the mass matrix. Now, modular invariance is particularly effective in constraining Yukawa coupling. So this central part here, this analytic part here. And indeed, by the transformation property of our matter fields, we see that if this term in the superpotential should be invariant, we need that Yukawa coupling transform in this way with an appropriate weight that should compensate the weight of the matter fields, okay? And with a suitable representation of the finite modular group in such a way that the product of all the representation that occur in this term here contains a singlet. Now, from a mathematical point of view, an object, an analytic function of tau that transforms in this way is called a modular form of level n and weight k. And the special and the most important property of this function is that they form a linear space of finite dimensions. So once the level and the weight are given, there are only finitely many modular forms of this type. And let me give you immediately an example of how we can exploit this feature in addressing the flavor problem. Suppose that, for instance, we work at level 3, where the finite modular group is the double covering of A4, and we assign the neutrinos of the 3 generation to a triplet of the finite modular group with weight 1. Okay. This means that in the superpotential, the Yukawa coupling should be a modular form of level 3 and weight 2 to compensate for the weights of neutrino. Okay. But mathematician told us that there are only 3 linearly independent modular forms of level 3, okay, and weight 2, that transform as a triplet of the finite modular group. And in practical terms, this means that the Yukawa couplings are completely determined as a function of tau up to an overall constant. So this is the most general expression for the Yukawa coupling that is allowed. Here, y1, y2, and y3 are known functions, okay, known analytic function. And moreover, as long as supersymmetry is unbroken, is exact, there cannot be any kind of correction to this result. So any kind of higher order operators that can modify this result. So you see that going back, this part, this holomorphic part of the mass matrix, in this particular example, is completely fixed with no free parameters apart from this overall constant. Okay. Now, with this ingredient, we can build a model of fermion masses. In particular, in the past, many models, especially of lepton masses, have been built. And these models are successful in reproducing neutrino square mass differences, mixing angles, and to predict the CP phases of the lepton sector in terms of two or three free parameters plus tau. Tau in these models is not predicted, if you wish, is just varied in order to maximize the agreement between theory and experiments, in order to maximize the agreement with the data. Okay. What are the drawbacks of this kind of approach? First of all, it is true that we have successful models, but we have too many models. There are more than 100 viable models that are due to the fact that we have a freedom in varying the different levels, in choosing the representation, and in varying the weights of the matter fields. Okay. Moreover, in all these models, in order to minimize the number of free parameters, the non-holomorphic contribution, so these, in principle, these matrices that contribute to derive the final mass matrix are assumed to be flavor universal in such a way that this contribution factorize and goes into an overall constant. But however, this is not the most general, if you wish, possibility that is allowed by modular invariance. So what can we learn from this exercise? Here you see in the tau plane, and in particular in the fundamental region of the modular group, the landscape of all these models. Each of these points correspond to a model, to a successful model, a model that can describe correctly neutrino masses and mixing angles. There are different colors because they refer to the different choice of the level. Okay. And already from this left picture, you see that this landscape appeared to be a particular one in the sense that, if you wish, these points are not completely random distributed in this region, but they try to cluster around some particular point or some particular region. And this tendency is even more pronounced if instead of considering all the possible models, we focus on the CP invariant models. What does it mean? That we start with the CP invariant theory, where the only source of CP violation is the modulus tau. Okay, when the modulus acquire a vacuum expectation, a generic vacuum expectation value, it breaks CP. If the only source of breaking of CP is tau, then we have this restricted selection of models. And you see that these appear to cluster around the imaginary unit. So what is special about this imaginary unit? So consider tau close to I. To work efficiently, we can use another set of coordinates in which instead of dealing with the tau, we use this coordinate u, that is equal to 0 when tau is equal to I. Moreover, you remember that I is left invariant by the S transformation, okay, and S acts on U, sending U into minus U. Okay, since U vanishes in tau equal to I, it is correct that essentially S is preserved in U equal to 0. Okay. If we are close to tau equal to I, this means that U can be treated as a small parameter, so we can expand our mass matrix in powers of U. And since at tau equal to I, we have this Z4 symmetry, you see that close to tau equal to I, the theory is like a Z4 invariant theory that is spontaneously broken by the symmetry breaking parameter U. And this conclusion is true independently on the chosen level. It is independent from the choice of representation on the weights and also on the choice of the kinetic terms. It is completely general. It has only to do with the fact that we are working close to tau equal to I. Okay. So if now we add to this completely general picture a single assumption that lepton doublets are assigned to an irreducible triplet of the finite modular group, then we can better specify the models. We will see that the models fall into three classes, and only one is particularly successful in reproducing neutrino masses and mixing angles. And these are the expressions of the mixing angles and neutrino masses in terms of x, which is essentially the size of u, of this small parameter. You see that M1 and M2 are close because they differ by a factor of order x. M3 is a big mass because it's 1 over x, okay? And so the model, this class of models predict a normal hierarchy in the neutrino sector. You also see that generically the atmospheric angle is large, and the solar angle deviate from the maximal angle by something of order x, and also the reactor angle is something small of order x squared. So everything goes in the right direction, and this result is completely general. It depends on the fact that we are close to tau equal to I, and is independent of any detail of the theory apart from this particular assumption. Okay. Let me come to the last topic of my seminar, so the solution to the strong CP problem. As we said at the beginning, we have a parameter which is this theta bar, which is a combination of the topological angle entering the QCD Lagrangian plus the phase of the determinant of the quark mass matrix. And the data tell us that this parameter should be extremely small, whereas we know that CP is broken by the CKM phase, which is a phase of order 1. Traditionally, the solution of this problem fall into two classes, if you wish. Either this parameter theta bar is promoted to a dynamical field, the axion that is relaxed to 0 at its vacuum expectation value. Okay, so we have a whole class of theory relying on this axion solution. Or on the other side, we assume that parity and CP are symmetries of the fundamental theory. So this theta term is forbidden in the theory. But then we should spontaneously break CP in such a way that we generate a CKM phase of order 1 at the same time we maintain this particular combination of phases extremely small. And example of a solution along this line are the so-called Nelson bar class of models. So the solution provided by modular invariance fall in this second class of solution. We assume that CP is a symmetry of the ultraviolet theory. So to start with, the topological angle is equal to 0. And if the only source of CP breaking, which should be spontaneous, is the phase associated with tau, then the physical parameter is nothing but the phase of the determinant of the Yukawa couplings in the quark sector. Now, we already saw that any matrix element in the matrix of Yukawa coupling is a modular form. Okay. Since the determinant is a polynomial in this entry, also the determinant is a modular form. Namely, the determinant transformed in this way under the modular group. It's a modular form with a particular weight, which is this combination of weights of fermion multiplets and X multiplet. Essentially, is the sum of the weights of the right-handed and left-handed quarks over the 3 generations. And also, we have a contribution from the weight in the X sector. Imagine for a moment that this weight, the weight of the determinant, is equal to 0. Now, it is a mathematical property that any zero-weight modular form is a constant. So if k is equal to 0, the determinant is a constant. And since our theory is a CP invariant, this constant should be a real constant. Okay. And since it is a real constant, if it is positive, then we have solved the strong CP problem. Okay, this theta bar is equal to 0. But have we any reason to believe that the weight of the determinant is equal to 0? And there is a very good reason, because if you look to the way which modular transformation acts on the fermion fields, when we go the basis in which these fermion fields are canonical, we see that the modular transformation is of this type. See, since this is a phase, the modular transformation is actually a local chiral transformation. Is a local transformation because here there is a tau dependence and tau is a fields that depend on x. So it is a local transformation. If it is a local transformation, it can give rise to anomalies. So better that we write down the condition for anomaly cancellation and we find a solution to these conditions. Now, by far the simplest solution for the cancellation of these mixed modular gauge anomalies, okay, is this one, that the weight in the x sector is equal to 0, and that for any, if you wish, a representation of in the fermionic sector, no, the weights are minus k, 0, and k, where k can be any integer. But if we take this solution and we plug back this solution into the previous expression for the weight of the determinant, we find that these contributions are independently equal to 0, they vanish, and so this weight is equal to 0. So the determinant is a real constant. If it is positive, the argument is 0, and the strong CP problem is solved. This is not the end of the story, because now we should provide an example in which not only theta bar is equal to 0, but also we can reproduce quark masses and especially a CKM phase, which is of order 1. Let me give you directly an example with a model in which the charges in the quark sector are given by -6, 0, and 6, no, referring to the 3 generation. And we find Yukawa coupling in the up and down quark sector that are of this type. These C are constant, are real constant, that are free parameters in this model. So we have plenty of free parameters, and with these free parameters, indeed, we can fit all quark masses, no, with constant of order 1. And moreover, we can also exploit the spontaneous CP violation in order to have a CKM matrix different from 0, actually of order 1, the correct CKM phase, despite of the fact that this particular texture have a determinant which is a real determinant. By the way, in this model, with the same assignment of weight, we can also fit the lepton sector. So I think that I was a little bit running. I can come to my conclusion, so there is some also time for question. We can say that the modular invariance, first of all, is a key ingredient also of the top-down approach, because it is an ingredient which is ubiquitous in string theory compactifications. So it can be analyzed both in the bottom-up and in the top-down approaches. Perhaps it is something to do with the missing principle that can help us in understanding and solving the flavor puzzle. We have seen that despite the fact that we have a variety of modular invariant models of lepton masses, all these models show a universal behavior when we are close to fixed points, and in particular when we are closer to tau equal to I, the models are successful in reproducing neutrino data, and they predict a normal ordering. We also saw that the strong CP problem can be solved via spontaneous CP violation. Of course, in a bottom-up approach, we have, as we saw, many possibilities, and so we don't know if we ever be able to make precise prediction. And in a sense, the situation resembles to what have been observed in the last century by this American photographer that taking many pictures of snowflakes, he observed that despite the fact that all the snowflakes share a sixfold symmetry, and not two of them are identical, but they are all different from each other. Thank you very much.
Thank you very much, Ferruccio. Thank you very much, Ferruccio, for the very nice talk. Thank you very much, Ferruccio, for the very nice talk. There are questions from the audience? Thank you very much, Ferruccio, for the very nice talk. Question from the audience?
Hi. Hi.
Yes, continue, Claudio.
Yes, thank you very much for such a nice talk. I was a bit lost in the last part where you said that you could solve the strong CP problem by this spontaneous CP, CP violation.
Yes.
But the strong CP problem says that the CP violation in the in the quark sector should be very, very small. So here it also comes very, very small. Why?
Yes, I go back to, sorry, I went too fast, maybe. Have a look to this particular pattern of Yukawa matrices in the quark sector, which is a prediction of modular invariance once we assign these weights. Okay. If we inspect this particular mass matrix, if you wish, Yukawa coupling, okay, there are constants, but there are also these E4 and E6 that are function of tau. So they carry phases. Carrying phases, they can give rise to the CKM phase. So in this particular example, we can generate a CKM phase, which is different from zero. Actually, it is of order 1 because generically the phases carried by these functions are of order 1. Despite of this particular feature, despite of the fact that CP is broken spontaneously and is broken by, let's say, order 1 elements, if you compute the determinant of this particular matrix, the determinant of this particular matrix is real. And you can say this, for instance, by, I don't know, by computing the determinant, exploiting this line, you see that you should multiply this. Essentially, the determinant is this times this, right, and this is the product of the elements that are along this anti-diagonal. Right. So despite of the fact that you have a phase of order 1 in these elements that generates the CKM phase, the determinant is simply the product of these 3 constants. And since the theory is CP invariant, so CP is only broken by the value of tau, these constants are real constant and the determinant is real. I don't know if if is more clear now.
Yes, yes, yeah. Thank you. Yes, I see. Right.
More questions? So Ferruccio, in your model, neutrino masses arrive from type 1 seesaw, or you had another mechanism to generate the masses?
Well, these models can the neutrino masses I'm referring to are let's say are Majorana masses, at least the ones that I have collected in this landscape, no? And are Majorana masses that can be generated either directly with the Weinberg operator or through the seesaw that can be a seesaw of type 1, type 2, type 3. However, also models with the Dirac masses have been conceived, and essentially the conclusions are the same. So there is a variety of ways in which you can describe neutrino masses that can even avoid or exploit the different type of seesaw.
Do you have prediction from leptogenesis?
So I think that these have been studied, but honestly, now I cannot remember them by heart. I remember that some group have also discussed leptogenesis and show that leptogenesis can be also accommodated within the type 1 seesaw. But even in the backup slides, unfortunately, I have no slide about leptogenesis, unfortunately. So I have nothing to add to this generic comment. Sorry.
Mm-hmm.
Thank you, Ferruccio. More questions from the audience? If there are no more questions, we thank Ferruccio for the very nice and very complete talk, and we'll be in the next seminar.
Thank you. Thank you very much again for the invitation, and I wish you all the best to all friends in Valparaiso.
Thank you very much, Ferruccio.
See you.
Ciao, ciao.
Ciao, ciao.